Let's start looking at LRC circuits. For now, in this lecture, we will look at the different components separately. So we'll look at a resistive load, meaning that we just have a resistor in an AC circuit. Then we'll look at the capacitor in an AC circuit, and then at the inductor. And in the next lecture, we're going to see how the three of them behave together in a circuit. Here we have the circuit for a resistive load. There is a resistor in a circuit with an alternating current power supply. So since the voltage fluctuates, the current will fluctuate as well. So it will basically go clockwise for a while and then counterclockwise. It's going to alternate directions based on the frequency. Then when we write Ohm's law, we will use the VRMS and IRMS given by the voltage and current in the circuit. So then we have VRMS is IRMS times R. Now, the resistor is a pretty easygoing fellow. It doesn't care whether current comes at it from the left or from the right. So no matter how the direction of the current is, whether it's going clockwise through here or counterclockwise, the resistor is constant. It just has the same value throughout. So the resistor doesn't change as a function of the frequency. So then if we want to look at the current through the resistor versus the voltage across the resistor, they are in phase with one another. So we have current and voltage being in phase with one another in the case of a resistor. Now, we're going to see later that it's hard to draw these diagrams. So there is another way of representing these sine waves, and that's called a phasor diagram. So here we have the current that is in phase with the voltage across the resistor. That's what we were indicating by the phasor diagram, that both current and the voltage are in phase with one another. And as they fluctuate here, they will basically rotate in these in this coordinate system. So here we have the omega t. Omega, remember, is 2 pi times the frequency. There's the same type of rotation here that there is oscillation over there. Now let's look at the capacitive load. So here we have a capacitor in a circuit where the power that's supplied fluctuates sinusoidally. Then we can write Ohm's law by using VRMS and IRMS. So we'll say that VRMS is equal to IRMS times this quantity, which is called the capacitive reactance. It is the way a capacitor reacts with a change of the current passing through an alternating current circuit. So X sub C is the capacitive reactance, and the shape of the graph of reactance versus frequency is this, because the capacitive reactance is 1 over 2 pi frequency times C. So we saw with the resistors that the resistor did not change at all as a function of frequency, but the capacitor does. So let's think about it. If the direction of the current doesn't change very frequently, so the frequency is low, that means that the current passes through quite a bit. The capacitor has a chance to charge, and the more charge it builds up, the less current it will let through. So that means that when the frequency is low, it will react quite heavily. So the capacitive reactance is going to be quite high when the frequency is low. But then if the direction of the current changes all the time, then charge never has a chance to build up across the capacitor. So that means that when frequency is high, the capacitive reactance is going to be low. So that's how we came about with this curve and that equation for the capacitive reactance. Another fun thing is that if you actually plug in the units in here, you end up with ohms, which we already assumed, since Ohm's law assumes that the voltage is in volts, current is in amps, and resistance is in ohms. Now, since the capacitor behaves differently, it has some sort of reaction to the alternating current, to the frequency of the current, then there is a phase difference between the current and the voltage across the capacitor. So how does this work? Well, first, in order for the capacitor to build charge and have a voltage across it, the current has to flow through the capacitor. So we'll say that the current comes first, it peaks first over here, before voltage gets a chance to build up. So we'll say that the current leads the voltage by pi over 2. So current has to flow through the capacitor before voltage can actually build up on the capacitor. So now when we draw the phasor diagram, we draw the current, and we know that the voltage lags by pi over 2. So that means that while the current is in the first quadrant, the voltage is going to be in the fourth quadrant. So this angle here is 90 degrees, and these two arrows are going to rotate in this coordinate system the way they fluctuate in this diagram. Now for the inductive load. So here we have an inductor in an AC circuit. Again, we can write Ohm's law, where VRMS is IRMS times the inductive reactance. So X sub L is the inductive reactance. And the way that the inductor behaves with a frequency change is like this. So the inductive reactance is 2 pi frequency times the inductance. So let's think about how inductors behave. If current goes through here, then the inductor all of a sudden experiences a current, which means that it's going to produce a magnetic field to oppose that current. Now, if the direction of the current is the same for quite a while, the inductor does get a chance to get used to that direction of the current, and it doesn't react very much. So when the frequency is low, then the inductive reactance is also low. But if the direction of the current changes frequently, if it goes back and forth like this, then the inductor has to constantly create a current to oppose that current trying to go through it, and it will react quite heavily. So that means that the inductive reactance is going to be high when frequency is high. Now the current through the inductor and the voltage across the inductor also are out of phase. So again, we have to remember that in order for voltage to build up across the inductor, a current has to flow through it. But the catch is here that the inductor produces its own current that counteracts the current. So the current will peak first, but in the opposite direction from the current that is pushed by the power supply. So that's why we have a maximum here for the current, but it's in the negative direction because it's in the opposite direction. So while current builds up first before voltage, but in the negative direction, we will say that the current lags the voltage, or the voltage leads the current by pi over 2. Again, in order to see this better, we draw the phasor diagram, and again here we have the current, and the voltage across the inductor is ahead of the current by pi over 2. So the voltage leads the current, it's already in the second quadrant, while the current is only in the first quadrant, and this angle here is 90 degrees. So this is how the different components behave in an AC circuit. We will see later on how they act together.